There's a tunnel beneath the Swiss-French border where magnets hum at temperatures colder than deep space, bending reality itself. Inside, protons circle 11,000 times per second, carrying energies that recreate the first breath of the universe. Sounds like progress, doesn't it? Here's the uncomfortable part. While these magnets generate fields 100,000 times stronger than Earth's own, something peculiar is happening overhead. Our planet's magnetic shield is developing weak spots, growing, accelerating in ways that make scientists nervous. The official line? Pure coincidence. Two completely unrelated phenomena. And that's probably true. Probably. But by the end of this, you'll understand why that word keeps appearing in safety assessments, and why nobody's quite sure what happens next. You'll want to subscribe and follow along, because we're diving into the space between what models predict and what experiments measure. The planetary changes exist. The operational timelines overlap, but the interaction mechanisms remain theoretical and carefully sidestepped in peer review. What CERN does in 2026 will either validate decades of assumptions or force us to reconsider everything. Picture this. Right now, beneath the border between Switzerland and France, there's a tunnel 27 kilometers long. Inside that tunnel, magnets are waking up. Not just any magnets. These are the most powerful magnetic fields ever created by human hands. And in 2026, they're about to get 50% stronger. The Large Hadron Collider is preparing for an upgrade that will push it into territory we've never explored before. And some people are asking a question that sounds like science fiction, but might not be. Could human physics break planetary physics? Let me paint the scene for you. Imagine standing at the entrance to CERN's underground facility. The air is cold, technical, humming with electricity. You descend into the Earth, and the temperature drops further. The tunnel stretches away in both directions, curved so gently you can't see the end. Along the walls, massive cylindrical structures pulse with a strange blue light. These are the superconducting magnets, cooled to temperatures colder than outer space, 1.9 Kelvin to be exact. That's minus 270, 1.25 degrees Celsius. At that temperature, strange things happen to matter. Electrical resistance vanishes, current flows forever, and magnetic fields become powerful enough to levitate metal objects, tear watches off wrists, and guide subatomic particles to speeds approaching the speed of light. The magnets at CERN operate at around 8.3 Tesla right now. That might not mean much to you, so let me give you some context. When you go for an MRI scan at a hospital, you're lying inside a magnet that produces about 1.5 to 3 Tesla. That's strong enough that technicians have to make absolutely sure you have no metal on your body. Now multiply that force by 3 or 4. That's where CERN operates today. But the high luminosity upgrade will push some magnets to 11 or 12 Tesla. These fields are so strong that if you got too close with anything ferromagnetic, it wouldn't just pull toward the magnet. It would accelerate so fast it could kill you. Now compare that to Earth's magnetic field. The planet we live on generates its own magnetic field that measures about 25 to 65 microtesla. CERN's magnets are roughly 100,000 to 200,000 times stronger than Earth's natural field. 100,000 times. That's not a small difference. That's the difference between a candle and a searchlight, between a whisper and a jet engine. The people who designed these magnets are brilliant. These superconducting systems are engineered to contain their magnetic fields locally. The field strength drops off according to what's called the inverse cube law. Essentially, if you double your distance from a magnet, the field strength doesn't just halve, it drops to 1/8. By the time you're at the surface, hundreds of meters up, it's negligible. The math says these fields should have absolutely no measurable effect on anything beyond CERN's immediate facility. But here's the thing about math. It's perfect in theory, and theory assumes we understand all the variables. CERN itself has done extensive modeling and safety reviews. The consensus is clear. There is no danger. But consensus isn't the same as certainty. Science is built on testing assumptions, on discovering what we didn't know. And when it comes to interactions between artificial magnetic fields of unprecedented strength and Earth's global magnetosphere, we're in territory where our models haven't been tested because we've never had fields this strong before. Let me be clear, I'm not suggesting CERN is going to destroy the Earth. What I am suggesting is more subtle and more interesting. Earth's magnetosphere isn't a static thing. It's a dynamic, flowing, constantly shifting system generated by churning molten iron 1,800 miles beneath our feet. This isn't a simple bar magnet. It's a complex, nonlinear system. And complex systems sometimes have properties that aren't obvious until you perturb them. There's something else happening right now that makes this conversation more than academic. Earth's magnetic field is changing. There's a region over the South Atlantic Ocean where the field is significantly weaker than it should be. It's called the South Atlantic Anomaly, and it's been growing. Satellites passing through this region experience higher levels of radiation. Between 1990 and 2020, the South Atlantic Anomaly weakened by about 15%, and it's accelerating. Here's where the timing gets eerie. CERN began low-power operations in 2008. Full energy collisions started in 2010, and all the while, the South Atlantic Anomaly has been growing. Now, I'm not saying there's a connection. The mechanisms aren't clear, but the human mind looks for patterns. And when we see two unprecedented things happening at roughly the same time, powerful artificial magnetic fields being created and Earth's natural field behaving strangely, we ask, could there be a link? The scientists at CERN would tell you no. They'd point to the physics, to the calculations, to the safety reports, and they'd probably be right. Probably. But science progresses by questioning, by testing, by admitting that our models are always approximations of reality, never reality itself. What makes this even more fascinating is that we're not just talking about magnets in isolation. The Large Hadron Collider accelerates protons to 99.9999991% of the speed of light. When two of these protons collide, they recreate conditions that last existed in the universe a trillionth of a second after the Big Bang. We're opening windows into realms of physics that are usually hidden from us. So the question isn't really whether CERN's magnets are going to flip Earth's poles tomorrow. The question is subtler and more profound. Are we absolutely certain we understand all the ways that extreme artificial fields might interact with natural planetary systems? Have we mapped every possible coupling, every feedback loop, every nonlinear effect? Or are we doing what humans have always done, pushing into new territory with confidence, born of incomplete knowledge? The magnets are waking up. The energies are rising. And we're about to find out if our understanding is as complete as we think it is. The Large Hadron Collider isn't just one magnet. It's a symphony of 1,632 superconducting magnets arranged in a ring 27 kilometers in circumference. The engineering alone is staggering. There are 1,232 dipole magnets, each 15 meters long and weighing 35 metric tons, creating the main magnetic field that bends the particle beams around the track. Then there are 392 quadrupole magnets, which focus the beams, squeezing them tighter as they circulate. The superconductivity is what makes this possible. At 1.9 Kelvin, niobium titanium cables become superconducting. Electrical resistance drops to exactly 0. The currents in these cables reach 11,800 amperes. For comparison, a typical household circuit might handle 15 to 20 amperes. These magnets are carrying currents more than 500 times larger. Try to do this with normal copper wire at room temperature, and the cables would melt almost instantly. When these magnets are operating, they store about 10 gigajoules of energy. That's equivalent to about 2.4 tons of TNT. That energy is locked in the magnetic field itself, and those field lines don't extend very far. The magnets are designed with a specific geometry that contains the field. This is where the inverse cube law comes in. For a dipole magnetic field, the strength decreases with the cube of the distance. At 2 meters, it's 1/8 as strong. At 10 meters, it's 1,000th. By the time you're 100 meters away, at Earth's surface directly above the tunnel, the field is millions of times weaker. But now let's talk about Earth's field. Earth is essentially a giant magnet, but it's nothing like the magnets at CERN. The magnetic field is generated by something called the geodynamo. Deep beneath us, starting about 2,900 kilometers down, is the outer core. It's liquid iron and nickel, heated to temperatures around 4,000 to 5,000 degrees Celsius. This molten metal is churning, convecting, driven by heat flowing out from the even hotter inner core. This motion generates magnetic fields through basic electromagnetism. The result is a magnetic field that extends far beyond Earth's surface. At the equator, the field's strength at ground level is about 30 to 40 microtesla. It's weak by laboratory standards, but enormous in scale. The field lines loop through space in vast arcs, extending tens of thousands of kilometers, creating the magnetosphere. Solar wind hits the magnetosphere and is deflected around us. Without this shield, the solar wind would strip away our atmosphere, just like it did to Mars billions of years ago. Earth's magnetic field is not static. It changes constantly. The field's strength varies. The positions of the magnetic poles drift. Every few 100,000 years, the poles reverse completely. The South Atlantic Anomaly is one manifestation of this chaos. It's a region where the field strength drops to 20 to 30 microtesla instead of the normal 40 to 50. That's enough to cause problems. Satellites experience higher doses of energetic particles. The International Space Station's orbit takes it through the region regularly, and astronauts receive higher radiation doses during those passes. What's causing the anomaly? The most likely explanation involves something called the African geophysical anomaly. Deep beneath Africa, there's a region where the mantle is hotter than usual, creating a massive upwelling that disrupts the flow of molten iron in the outer core nearby. Some scientists think this might even be the beginning of a magnetic pole reversal. Now here's where things get psychologically interesting. The South Atlantic Anomaly is real and growing. CERN's magnets are real and intensifying. The human mind sees these two things and immediately starts looking for connections. It's pattern recognition, one of our most fundamental cognitive abilities. The challenge is distinguishing genuine correlations from spurious ones. The physicists say no connection is possible. The fields don't extend far enough. The inverse cube law is inviolable. And they're almost certainly right. But almost certainly isn't absolutely certainly. Have we actually measured the field strength at various distances from CERN during full power operation? Have we looked for any anomalous effects in the ionosphere above the facility? As far as I can tell, most of these measurements haven't been done because the consensus view is that they're unnecessary. This is where a curious tension emerges. Science is supposed to be empirical, based on observation and experiment. But when the theoretical case seems airtight, we often don't do the experiments. History is littered with examples of theories that seemed bulletproof until someone actually did the experiment. The ether was supposed to permeate all of space until the Michelson-Morley experiment found nothing. The universe was supposed to be slowing down until observations showed it's accelerating. So maybe the question isn't whether CERN's fields can affect Earth's magnetosphere. Maybe the question is, have we looked carefully enough to be sure they don't? There's a sociological dimension here. Proposing to study something that sounds like a fringe idea can be career suicide. So certain questions don't get asked. And that creates a blind spot. Maybe the assumptions are right, but maybe there's something happening in that unexplored space that would surprise us. There's something profoundly human about the fear of powerful machines. We've been afraid of our own inventions since the first wheel rolled faster than expected. This fear isn't irrational. It's a recognition that when we build something powerful, we don't always understand all the consequences. The Industrial Revolution gave us steam engines, and also pollution and climate change. Nuclear fission gave us clean energy, and also Hiroshima and Chernobyl. So when people look at CERN and feel a twinge of anxiety, that's not stupidity. That's wisdom. The question is whether that anxiety is proportional to the actual risk, or whether we're projecting our general fear of the unknown onto a specific target. Let me introduce you to chaos theory. In the 1960s, meteorologist Edward Lorenz was working on weather prediction models. One day, wanting to examine a sequence more carefully, he restarted a simulation from the middle. He typed in conditions from a printout that showed 3 decimal places. The computer, internally, was using 6 decimal places. That tiny difference should have caused only a tiny divergence. But Lorenz found something shocking. Within a short time, the weather patterns were completely different. A minute change in initial conditions led to a massive change in outcome. This became famous as the butterfly effect. Weather is chaotic. That's why we can't predict it more than about 10 days in advance. The atmosphere follows the laws of physics perfectly. But the sensitivity to initial conditions means that microscopic variations eventually blow up into completely different weather patterns. Now here's the uncomfortable question. Is Earth's magnetosphere a chaotic system? The geodynamo operates in a regime where fluid dynamics, electromagnetism, and heat transport all interact non-linearly. Non-linear means that doubling the input doesn't double the output. Fluid turbulence is inherently chaotic, so it's plausible that the core's behavior has some chaotic characteristics. If so, small perturbations might, under the right conditions, lead to large effects. Let's be absolutely clear. There is no evidence that CERN's fields are perturbing the core. The distances are enormous. The fields are localized. But the human mind looks at a chaotic system and asks, what if? These are wild speculations. They're almost certainly wrong, but that word almost is doing a lot of work. In the late 1800s, physicists were confident they understood matter and energy. Lord Kelvin said there were only 2 small clouds on the horizon of physics. Within 30 years, those 2 clouds had overturned all of classical physics and given birth to relativity and quantum mechanics. The lesson isn't that chaos theory will overturn electromagnetism. The lesson is that complex systems can surprise us. Physics systems are generally more predictable because they follow precise mathematical laws. But precise laws can still produce unpredictable behavior if the system is chaotic. The Earth system is definitely complex. There are feedbacks everywhere. Ice reflects sunlight, cooling the planet, causing more ice. Clouds trap heat, but also reflect sunlight. We know that human activities can have planetary scale effects. Carbon dioxide mixes throughout the atmosphere in months. So the question is whether CERN's magnets could possibly be one of those perturbations. The honest answer is almost certainly not. But the measurements to be absolutely sure haven't all been done. And that tiny gap between almost certainly and absolutely is where fear lives. There's a psychological concept called the availability heuristic. We judge probability based on how easily we can imagine something. Plane crashes are rare but vivid, so people overestimate their likelihood. CERN captures the imagination. Giant underground machine. Insane energies. It feels dangerous. So even though the actual risk is 0 according to every calculation, the feeling of risk persists. This is also why conspiracy theories flourish around CERN. A conspiracy theory is a pattern recognition error. The mind sees events, searches for a cause, and latches onto something emotionally satisfying. CERN fits that mold perfectly. It's elite science, funded by governments, operating machinery most people will never see. It's the perfect conspiracy theory target. Yet, underneath the conspiracy thinking, there's sometimes legitimate curiosity. What are the limits of our knowledge? If we're honest, those boundaries exist everywhere in science. We don't fully understand turbulence. We don't fully understand consciousness. We don't fully understand dark matter or dark energy. So why would we expect to fully understand every possible interaction between a powerful artificial system and a complex planetary system? The challenge is balancing healthy skepticism with paranoid fantasy. Now let's zoom out to something even more fundamental and unsettling. What if the problem isn't the strength of CERN's magnets at all? What if the real question is about the nature of reality itself? Because when you start colliding particles at ultra-high energies, you're probing the structure of the vacuum, and the vacuum might not be as empty as it sounds. In quantum field theory, the vacuum isn't nothingness. It's a seething foam of virtual particles constantly popping into and out of existence. This leads to a fascinating and terrifying idea: vacuum metastability. Imagine a marble sitting in a bowl on a table. The marble is stable, but if the bowl is sitting on a hillside, the marble is only metastable. If you gave it enough energy to get over the lip, it would roll down to a much lower position. Some theoretical models suggest our entire universe might be in a metastable state. The Higgs field, which gives particles mass, might be sitting in a local minimum rather than the absolute minimum. If that's true, then something could kick the Higgs field into a lower energy vacuum state. Once that happened, the change would spread at the speed of light in an expanding bubble. Everything inside would have different physics. The universe as we experience it would cease to exist. This is called vacuum decay. Stephen Hawking, in his final book, mentioned it and called it perhaps the greatest threat to the universe. He wasn't saying it's imminent. He was pointing out that theoretical scenarios exist where the universe could end with a silent transformation, spreading at light speed, erasing everything in its path. Could CERN cause this? The answer is almost certainly no. First, cosmic rays hit the atmosphere at energies thousands or millions of times higher than anything CERN can produce. The Earth has been absorbing these impacts for 4.5 billion years. If ultra-high energy collisions could trigger vacuum decay, it would have happened already. Second, vacuum decay would require energies at the Planck scale, around 10 to the 19 giga-electron volts. The LHC operates at 14 tera-electron volts. That's 15 orders of magnitude lower. Third, the Higgs boson discovery in 2012, with a mass of about 125 giga-electron volts combined with other measurements, tells us our vacuum is either stable or metastable with an incredibly long decay lifetime. So even if it's technically metastable, it's irrelevant. But despite these reassurances, the question gets asked. Because the consequences, if we're wrong, are absolute. So even if the probability is vanishingly small, the sheer magnitude of the consequence means people wonder. There's another controversial topic: micro black holes. In some theoretical models with extra dimensions, the energies at the LHC might be high enough to create tiny black holes. These would be microscopic, with lifetimes measured in tiny fractions of a second. According to theory, they would immediately evaporate through Hawking radiation. When this possibility was first raised, it caused public concern. What if one didn't evaporate? What if it fell to Earth's center and started eating matter? Again, the physicists have solid answers. Hawking radiation is a robust prediction. A micro black hole would evaporate in 10 to the minus 23 seconds. Moreover, cosmic rays have been creating micro black holes, if they exist at all, for billions of years. We're still here. But the fear persists because the stakes feel so high. There's a psychological asymmetry. When experts say something is safe, people hear probability. When they say something could be dangerous, people hear certainty. We're wired to overweight threats. Modern life is full of risks we're terrible at assessing. We worry about airplane crashes, but not car crashes. CERN feels scary to many people, even though the actual risk is effectively zero. So when we talk about vacuum decay or micro black holes, we need to separate several things. What does the physics say? These scenarios are either impossible or so unlikely they're not worth worrying about. Have we done enough experiments? Yes. Why do people worry anyway? Because humans are bad at risk assessment, and because admitting we don't know everything leaves room for imagination to run wild. Let's talk about the elephant in the room. If you spend any time online looking at discussions about CERN, you'll quickly fall into a rabbit hole of conspiracy theories. Some are relatively tame, others are absolutely bonkers. The tame ones focus on things we've already discussed. Worries about magnets affecting Earth's field, concerns about triggering vacuum decay, fears of micro black holes. These aren't conspiracies. They're misunderstandings of physics, but they come from a place of genuine curiosity and concern. The bonkers ones go much further. There are people who believe CERN is intentionally trying to open portals to other dimensions. They point to the fact that CERN's logo contains what looks like a 666, the number associated with the devil in Christian theology. They note that a statue of Shiva, the destroyer, stands outside CERN's main building, a gift from the Indian government when India joined CERN as an observer state. They highlight that the collider's location near Geneva puts it close to old medieval descriptions of gateways to the underworld. They splice together imagery of particle collisions, demonic symbolism, and quotes taken out of context from scientists talking about testing extreme physics. The resulting narrative: CERN is engaged in some kind of occult ritual disguised as science, attempting to tear holes in reality and invite malevolent entities into our world. This is where we leave the realm of science and enter pure fantasy. There is no physical mechanism by which smashing protons together could open a portal to another dimension, at least not in any literal sense. Sure, string theory and other speculative models propose extra-spatial dimensions beyond the three we experience. If those exist, high-energy collisions might produce effects that indirectly reveal them. But that's not the same as creating a doorway you could walk through. It's detecting subtle deviations in particle behavior that would be consistent with energy leaking into hidden dimensions. The math is complicated, the experiments are precise, and there are no demons involved. So why do these theories exist? Part of it is a fundamental misunderstanding of metaphor in science. Physicists use language creatively. They talk about particles as if they have personality. They name things like strange quarks and charm quarks, or the God particle, which is a media nickname for the Higgs boson that physicists themselves generally dislike. When a scientist says they're probing the fabric of space-time, they mean studying the geometric structure of the universe using mathematical models and experimental data. They don't mean literally tearing reality like you'd rip a piece of cloth. But if you don't understand the metaphor, the language can sound ominous. Another part is projection. Science operates in a realm most people don't have access to. The mathematics of quantum field theory is years of graduate study beyond what even most physics undergraduates learn. The experimental techniques involve billion-dollar machines and international collaborations. There's a sense of alienation, of being excluded from knowledge, of decisions being made by elites without public input. And when people feel excluded, they sometimes construct alternative narratives that put them on the inside. If CERN is doing secret occult rituals, then the real knowledge isn't in the equations. It's in decoding the symbols, connecting the dots, seeing the patterns that the experts are either missing or hiding. It's a way of reclaiming agency. But beneath the absurdity, there's sometimes a legitimate question. Are there things we don't know? Absolutely. Are there risks we might not have fully assessed? Potentially, though none that evidence supports. Is it possible for experts to be wrong? Of course. The history of science is full of overturned paradigms. So the conspiratorial thinking, while wrong in its specifics, is tapping into a real anxiety. The anxiety that the people in charge might not have everything figured out. Let's distinguish between conspiracy theories and legitimate uncertainties. A conspiracy theory posits intentional deception or malice. It requires that large numbers of people coordinate to hide the truth, and that the truth, if revealed, would be shocking or catastrophic. The problems with conspiracy theories are manifold. First, large conspiracies are nearly impossible to maintain. People talk. Whistleblowers emerge. Documents leak. Second, conspiracies assume competence that organizations rarely have. Governments and corporations are often incompetent, not masterfully deceptive. Third, conspiracies usually attribute agency to events that are better explained by incompetence, accident, or emergent complexity. Fourth, conspiracies are unfalsifiable. Any evidence against them is dismissed as disinformation. Any lack of evidence is proof of the cover-up. Legitimate uncertainties, on the other hand, are parts of science where we genuinely don't have complete answers. These aren't hidden. Scientists write papers about them. Conferences are dedicated to them. They're questions like, what is dark matter? How do neutrinos get mass? Is there physics beyond the standard model? What happens to information that falls into a black hole? Is our vacuum stable or metastable? These are real open questions. The answers matter, and scientists are actively working on them. CERN itself is a tool for addressing some of these questions. The discovery of the Higgs boson was a triumph, confirming a prediction made decades earlier. But it also opened new mysteries. The Higgs mass is close to a value that makes our vacuum potentially metastable. That's not a danger. It's a clue. It tells us something about the underlying structure of the theory. Similarly, the standard model doesn't include dark matter or explain the matter-antimatter asymmetry or incorporate gravity at the quantum level. These gaps are where the frontier of knowledge lies. Every experiment at CERN is probing those gaps, looking for deviations from the standard model that would point toward new physics. One area where legitimate uncertainty exists is in the detailed modeling of magnetohydrodynamics in the Earth's core. We have a general understanding of the geodynamo. We know it's driven by convection, influenced by rotation, and generates the magnetic field. But the precise flows of molten iron at any given moment, the interaction between the solid inner core and liquid outer core, the effects of the mantle above, all of these involve equations that are too complex to solve exactly. We use computer simulations, but those simulations make approximations. They can't capture every scale of turbulence. They can't include every physical process. So there's irreducible uncertainty. Does this mean CERN could secretly be affecting the core? No. The energy scales are all wrong. The distances are too great, but it does mean that our models of the core are imperfect, and imperfect models sometimes surprise us. The same is true of the magnetosphere. Satellite observations have revealed structures we didn't predict. Magnetic reconnection events, substorms, plasma waves, all behaving in ways that required updating our models. The magnetosphere is an active area of research, not a closed book. There's also legitimate uncertainty in the climate system, not about whether climate change is happening or whether it's caused by humans. Both of those are well established, but about the precise regional impacts, the timing of tipping points, the feedback loops that might accelerate or slow the process. Earth is a complex system. We're learning more every year, but we're far from omniscient. And into that uncertainty, conspiracy theories can insert themselves. Some people claim CERN is affecting weather patterns. They point to unusual storms or temperature records and correlate them with CERN operations. Again, there's no mechanism. The energies involved are contained. The fields don't reach the atmosphere, but the human mind sees correlations and leaps to causation. This is especially true when the events are dramatic. A major storm hits, people suffer, and the mind searches for something to blame. Better to blame a shadowy science facility than to confront the uncomfortable truth that sometimes nature is just chaotic and destructive. What about micro black holes escaping? Some conspiracy theorists claim that if CERN creates a micro black hole and it doesn't evaporate instantly, it could sink to the Earth's center and begin consuming matter. We've already addressed why physics says this can't happen. But let's engage with the emotional core of the fear. The idea of something invisible, unstoppable, eating the planet from within is primally terrifying. It's like a cancer of the cosmos. And unlike sudden catastrophes that are over quickly, this would be slow. You'd know it was happening. You'd watch the ground crack, volcanism increase, earthquakes proliferate. It would be apocalyptic in slow motion. This fear taps into something deep. We're afraid of losing control, of invisible threats, of mistakes that can't be undone. Radiation after Chernobyl. Microplastics in the food chain. PFAS in the water. These are real examples of human activity creating invisible, pervasive problems. So when people worry about CERN, part of what they're worrying about is the general pattern. Humans do something they think is safe. Something goes wrong, and by the time we realize it, it's too late to fix. That pattern is real. It has happened. Just not with particle physics. The physics is too well understood, the precautions too extensive, the cosmic ray argument too airtight. But here's where it gets philosophically interesting. How do we know when we know enough? How do we decide that a risk is low enough to proceed? In engineering, we use factors of safety. If a bridge needs to support 10,000 pounds, you design it to support 50,000. But with fundamental physics, what's the appropriate safety factor? If calculations say the probability of vacuum decay is 10 to the minus a billion, is that safe enough? What if it's 10 to the minus a million? 10 to the minus 1,000? At what point do we say the risk is acceptable? Society makes these decisions all the time, often implicitly. We accept a certain rate of traffic deaths as the cost of having cars. We accept a certain rate of construction accidents as the cost of building infrastructure. We don't shut down civilization because there are risks. But with something like CERN, where the potential consequences, if the models are wrong, could be existential, does the calculus change? Most philosophers and scientists would say no. We follow the evidence. The evidence overwhelmingly supports safety. But there's always someone asking, what if we're missing something? And that question, in a sense, can never be fully answered. Because the unknown unknowns, by definition, are unknown. We can't prove there isn't some physical phenomenon we haven't discovered yet that would change the risk assessment. We can only say, based on everything we know, which is a lot, the risk is negligible. The conspiracy theories, then, are a distorted mirror of legitimate epistemological uncertainty. They take the kernel of truth, that we can never be absolutely certain about anything, and blow it up into apocalyptic narratives, unsupported by evidence. The challenge for science communication is walking the line between honest acknowledgement of uncertainty and giving fuel to unfounded fears. It's easier to just assert certainty, to say CERN is safe, period, end of discussion. But that's not intellectually honest. And it's also counterproductive because people can sense when they're being patronized. Better to admit the limits of knowledge while also clearly stating what the evidence shows. The evidence shows CERN is safe. There are theoretical uncertainties in other areas of physics, but those uncertainties don't translate into credible risks from particle collisions. It's a nuanced message. Nuance doesn't make good headlines, but it's the truth. Now let's lift our eyes from the underground tunnels of CERN and the churning iron core of Earth and look outward. Because while humans build powerful machines on our planet's surface, the universe has been conducting experiments at energies and scales we can barely imagine since the beginning of time. And sometimes, those experiments come to visit us. In January 2025, astronomers confirmed something extraordinary. An object that entered our solar system from interstellar space was actively outgassing, behaving like a comet. This object, designated 3I Atlas, is only the third confirmed visitor from beyond our solar system that we've detected. The first was Oumuamua in 2017, a tumbling, elongated object that accelerated as it left the sun, possibly from outgassing, though none was directly detected. The second was 2I Borisov in 2019, which looked and behaved exactly like a regular comet, complete with a tail and coma. And now, 3I Atlas. Why does this matter? Because every interstellar object tells us something about the galaxy beyond our tiny neighborhood. Our solar system is just one of hundreds of billions of star systems in the Milky Way. Most of them are so far away, we'll never visit them. But occasionally, material from those distant systems gets ejected and wanders through the galaxy for millions or billions of years. When one of those wanderers happens to pass close enough to the sun, we get a chance to study material that formed around a different star, under different conditions, possibly billions of years ago. It's like finding a message in a bottle from another world. 3I Atlas is particularly interesting because of its composition. Spectroscopic analysis by the James Webb Space Telescope and ground-based observatories shows that its ice is rich in carbon dioxide and carbon monoxide, similar to comets from the outer solar system. But there are also subtle differences in trace molecules that suggest it formed in a colder environment or at a different time in its home star's evolution. It's a chemical fingerprint from another world, and scientists are racing to decode what it means. The trajectory of 3I Atlas is hyperbolic, meaning it's moving fast enough that the sun's gravity can't capture it. It came from the direction of the constellation Ursa Major, though tracing its path backward through the galaxy is complicated because it's been traveling for potentially millions of years. And during that time, the stars have moved. It's possible, though uncertain, that it originated from a star system that no longer exists, perhaps one whose star went supernova, or whose planets were disrupted by a close encounter with another star. In that sense, 3I Atlas is an orphan, carrying the memory of a lost world. What makes interstellar objects philosophically fascinating is that they remind us how vast and full the universe is. The fact that we've only detected 3 objects so far doesn't mean there are only 3. It means most of them are too small, too fast, or on trajectories too far from Earth for us to notice. The Vera C. Rubin Observatory, which began operations in Chile in 2025, is expected to detect dozens or even hundreds of interstellar objects over the next decade. Each one will be a snapshot of a different part of the galaxy, a different chemical environment, a different history. Some researchers speculate about the possibility of interstellar panspermia. The idea, first proposed seriously in the 1970s by Fred Hoyle and Chandra Wickramasinghe, is that life might spread through the galaxy not by intelligent civilizations sending spacecraft, but by microbes hitching rides on comets and asteroids. If a planet with life gets hit by a large asteroid, debris is ejected into space. Some of that debris might contain microbes trapped in ice or rock. Those microbes could survive the radiation and cold of space if they're dormant. If the object eventually crashes into another planet with suitable conditions, the microbes could revive and seed that new world. It sounds like science fiction, but it's not entirely implausible. We know some microbes can survive extreme conditions. Tardigrades, for example, can withstand radiation doses that would kill almost any other complex organism, and they can survive the vacuum of space for limited periods. There's no evidence that 3I Atlas carries life or ever did, but the speculation highlights how little we know about what's out there. The galaxy is old, 13 billion years or more. Stars have been forming and dying for all that time. Planets have been born and destroyed. Material has been recycled over and over. The atoms in your body were forged in stars that died before the sun was born. The oxygen you breathe came from stellar nucleosynthesis billions of years ago. In a very real sense, we are made of stardust. And objects like 3I Atlas are reminders that the universe is one big interconnected web, with material flowing between stars, galaxies evolving and colliding, and time stretching back so far that our entire civilization is less than a blink. This perspective matters when we think about CERN and human experiments. Yes, we're building powerful machines. Yes, we're probing energies and fields at the extremes of what's possible on Earth. But the universe has been doing this kind of thing naturally since forever. Supernovae release energies that dwarf anything we can imagine. Neutron star collisions generate magnetic fields so strong they would disrupt atomic bonds. Quasars blast out jets of particles at nearly the speed of light, powered by supermassive black holes. Cosmic rays hit our atmosphere every second, with energies far beyond the LHC. We're not creating anything the universe hasn't already created countless times. We're just doing it in a controlled environment where we can measure and study it. In 2025, the European Space Agency's Comet Interceptor mission passed a major milestone in preparation for its launch. This mission is designed not to chase a comet we've already identified, but to wait in space and intercept a truly pristine comet, one that's entering the inner solar system for the first time. These are the most primitive objects accessible to us. They've been in cold storage in the Oort cloud for 4.5 billion years, unchanged since the solar system formed. When Comet Interceptor reaches its target, whenever that happens in the late 2020s or early 2030s, it will analyze material that's a direct sample from the solar nebula, the cloud of gas and dust that collapsed to form the sun and planets. What's the connection to CERN? At first glance, none. But thematically, both are about probing origins. CERN collides particles to recreate conditions from the first moments after the Big Bang, trying to understand what the universe was like when it was a trillionth of a second old. Comet Interceptor will study material that's been frozen since the solar system was young, trying to understand what conditions were like when Earth was forming. Both are acts of cosmic archaeology, and both remind us that the past is encoded in the present if we know how to read it. Subatomic particles remember the Big Bang. Comets remember the solar nebula. We live in a universe where history is everywhere, written in the fabric of space, in the chemistry of ice, in the ratios of isotopes in ancient rocks. One of the enduring mysteries in comet science is non-gravitational acceleration. Some comets, as they approach the sun and start outgassing, experience small changes in their orbits that can't be explained by gravity alone. The escaping gas acts like a tiny rocket, pushing the comet in unpredictable directions. Oumuamua famously showed this behavior, which led to wild speculation that it was an alien spacecraft adjusting its trajectory. The much simpler explanation is outgassing, even though no gas was directly detected. The signal was just below our instrument's sensitivity, but the non-gravitational acceleration was measurable. 3I Atlas also shows this effect. As it swings around the sun, jets of gas escape from specific spots on its surface, heated by sunlight. Those jets push the comet in complex ways. Predicting its exact future trajectory requires modeling not just gravity, but also the thermodynamics of ice sublimation, the rotation of the nucleus, the distribution of volatile materials. It's a messy problem, full of uncertainties. And that's just one comet. Imagine trying to predict the behavior of billions of them over millions of years. You quickly realize how much of the solar system's history is dominated by chaos and contingency. This connects back to our earlier discussion of complex systems. The solar system isn't a clockwork mechanism. It's a dynamic, evolving, sometimes chaotic system. Comets get deflected by Jupiter. Asteroids collide and fragment. Orbits shift over millennia. The same is true of Earth's climate, of ecosystems, of the geodynamo. Complex systems defy simple prediction. That's not a failure of science. It's a recognition that some things are inherently unpredictable, not because we lack knowledge, but because the systems themselves are sensitive to initial conditions in ways that make long-term forecasting impossible. And yet, we try. We build models. We launch missions. We collect data. Because even if we can't predict everything, we can understand the general principles. We know comets are icy because we've analyzed their spectra. We know their orbits are shaped by gravity and outgassing. We might not know exactly where 3I Atlas will be in 1,000 years, but we know it's leaving the solar system and will wander the galaxy until it encounters another star, maybe millions of years from now. That's enough. Perfect knowledge isn't required for meaningful understanding. The same applies to CERN. We might not be able to predict every detail of every collision. Quantum mechanics forbids that. The Heisenberg uncertainty principle is fundamental. But we can predict the statistical behavior of trillions of collisions. We can search for patterns, for anomalies, for hints of new physics. And that's exactly what scientists do. They're not looking for confirmation of what they already know. They're looking for surprises, because surprises are where discoveries happen. 3I Atlas is a surprise, an object from beyond, carrying secrets we're only beginning to unravel. In a few years, it will be too faint to observe, too far from the sun, heading back into the dark between stars. But the data will remain. Scientists will study it for decades, comparing it to future discoveries, building a picture of what the galaxy is like beyond our little corner. And maybe, just maybe, one of those future objects will be truly alien, not in the sense of carrying life, but in showing us chemistry or physics we've never seen before. Something that makes us rethink our models, our assumptions, our place in the cosmos. That's the hope. That's why we look up. Not because we're afraid, but because we're curious. And curiosity is the most human thing there is. Let's bring this full circle with one of the most unexpected developments in science over the past few years: artificial intelligence. You might think AI and astronomy have nothing to do with each other. One is about computers. The other is about stars. But in 2025, a study published in Nature Astronomy showed that large language models, the same technology powering chatbots and text generators, can classify cosmic events with remarkable accuracy from just a few examples. This is a big deal. Let me tell you why. Astronomy generates absurd amounts of data. The Vera Rubin Observatory, which I mentioned earlier, will photograph the entire visible sky every few nights. It will detect millions of transient events like supernova, asteroid flybys, variable stars, and more. But most of those events aren't interesting. A supernova is interesting. A known asteroid passing by for the 1,000th time is not. The challenge is sorting the wheat from the chaff, identifying the rare, genuinely novel events buried in oceans of routine data. Traditionally, this required human experts laboriously classifying thousands of examples to train machine learning algorithms. It was slow, expensive, and limited by human availability. Enter large language models. These are AI systems trained on vast amounts of text from the internet, learning patterns in language, context, and information structure. It turns out they can generalize surprisingly well to non-language tasks if you give them the right prompts. Researchers showed an LLM a handful of examples of cosmic events like supernovae, gamma ray bursts, and tidal disruption events, along with descriptions of their properties. Then, they asked the AI to classify new, unlabeled examples. The accuracy was comparable to traditional machine learning methods that require orders of magnitude more training data. It's not perfect, but it's good enough to be useful. And it democratizes the process. You don't need a team of experts manually labeling data for weeks. You need a few examples and a sufficiently powerful AI. This is part of a broader trend. AI is becoming a tool for scientific discovery in ways that weren't possible even 5 years ago. In particle physics, neural networks help identify rare particle decay signatures in the billions of collision events at CERN. In drug discovery, AI predicts protein folding and designs molecules that could be new medicines. In climate science, AI models learn to predict weather patterns and extreme events from satellite data. The technology is accelerating research across every field that deals with large, complex datasets, which is basically every field now. But AI also raises questions. How do we trust results we don't fully understand? When a neural network identifies a supernova, it's not telling us why it thinks that's a supernova. It's just outputting a classification based on patterns it learned. If it's right, great. If it's wrong, we might not know unless we double-check manually. This is called the black box problem. The AI works, but we can't peer inside and see its reasoning. It's like having an oracle that gives correct answers but can't explain itself. Useful, but unsettling. There's also the question of bias. AI systems learn from the data they're trained on. If that data is biased, the AI will be biased. In astronomy, if most supernova training examples come from nearby galaxies, the AI might miss supernovae in distant, unusual galaxies because they look different. In particle physics, if the training data includes only standard model processes, the AI might dismiss genuinely new physics as noise. Researchers are aware of these issues and design experiments to mitigate them, but the risk is always there. The AI is a tool, not a replacement for human judgment. It helps us see patterns we'd miss, but it can also blind us to anomalies if we rely on it too much. In 2025, AI also contributed to the discovery of several new exoplanets, planets orbiting stars other than the Sun. The transit method, where we watch for tiny dips in a star's brightness as a planet passes in front, generates light curves for thousands of stars simultaneously. An AI trained to recognize transit patterns can scan through those light curves far faster than humans, flagging candidates for follow-up. Some of these candidates turn out to be false positives. Others are genuine planets. And a few are bizarre systems that don't fit our models, like planets orbiting backwards or stars with multiple planets in resonant orbits that shouldn't be stable. These oddball systems are where the interesting science happens. They force us to refine our theories of planet formation and orbital dynamics. The synergy between AI and astronomy is a reminder that progress often comes from unexpected combinations. Who would have thought that software designed to generate coherent text could also classify cosmic explosions? But that's how breakthroughs happen. Tools developed for one purpose turn out to be useful in another. The internet was built for communication and quickly became a platform for science, commerce, and culture. The microwave was invented as a side effect of radar research. Velcro came from studying burrs that stuck to a dog's fur. Serendipity and cross-pollination of ideas are how innovation works. This connects to CERN in a profound way. The World Wide Web was invented at CERN in 1989 by Tim Berners-Lee, a physicist who wanted a better way for researchers to share data. He created a system of hyperlinked documents accessible through a browser. That system became the foundation of the modern internet. Billions of people use it every day without knowing its origins. CERN wasn't trying to revolutionize communication. They were trying to solve a practical problem. How do you share gigabytes of data among thousands of scientists spread across the globe? The solution they invented changed the world. The same could be true of future discoveries at CERN. Maybe the next energy upgrade will find something unexpected. Maybe there's a particle beyond the standard model that opens up entirely new physics. Maybe there's a subtle effect in the Higgs field that points toward quantum gravity. We don't know. We can't know until we look. But history suggests that when you push into new regimes, you find new things. And those new things often have implications far beyond the original question. Consider the Higgs boson itself. It's a fundamental particle, yes, but it's also a clue about the structure of the universe. The Higgs field fills all of space, giving mass to other particles through their interaction with it. Without the Higgs field, electrons, quarks, and other particles would be massless and couldn't form atoms. There would be no chemistry, no stars, no planets, no life. The Higgs field is essential to existence itself. Discovering the Higgs wasn't just checking a box on the Standard Model. It was confirming a deep truth about why the universe is the way it is. What if the next discovery is equally profound? What if we find evidence of extra dimensions, or supersymmetry, or a new force of nature? Any of those would reshape our understanding of reality at the most fundamental level. And unlike past revolutions in physics, which took decades to filter into technology and culture, modern discoveries spread almost instantly. The Higgs discovery in 2012 was global news within hours. The first image of a black hole in 2019 went viral. Science is part of our collective consciousness now in a way it wasn't a century ago. That's both exciting and challenging. Exciting because it means public engagement with science. Challenging because it means misinformation and fear-mongering spread just as quickly as real knowledge. The role of AI in communicating science is another frontier. Language models can translate technical papers into accessible language, answer questions about complex topics, and even generate educational content. But they can also hallucinate facts, present speculation as certainty, and reinforce existing biases. Navigating that landscape requires critical thinking, a skill that's harder to teach than it should be. People need to understand not just scientific facts, but the process of science. How evidence is gathered, how theories are tested, how uncertainty is quantified. That's not something most people learn in school, and it shows in public discourse. When a news headline says scientists discover X, the public often hears X is true. When what the scientists actually said is, we found evidence consistent with X, which needs further testing. That gap between communication and understanding is where confusion breeds. As we look toward the future, the combination of powerful experiments like CERN, vast observational campaigns like Rubin Observatory, and advanced AI tools promises an era of discovery unlike anything in history. We're poised to answer questions about dark matter, dark energy, the matter-antimatter asymmetry, and the ultimate fate of the universe. These aren't just academic puzzles. They're about understanding where we came from, what we're made of, and where we're going. They're about our place in the cosmos. But with that power comes responsibility. Every new technology, every new capability brings ethical questions. Who decides how these tools are used? Who benefits from the discoveries? How do we ensure that advances in fundamental science translate into improvements in human welfare, not just more powerful weapons or greater inequality? These aren't easy questions. They require input from scientists, ethicists, policymakers, and the public. They require humility, recognizing that we don't have all the answers, and that some answers might be uncomfortable. The story of CERN, of particle physics, of astronomy, of AI, is ultimately a human story. It's about curiosity, the drive to know, the refusal to accept ignorance. It's about collaboration, thousands of people from dozens of countries working together on problems too big for any one person or nation. It's about perseverance, spending decades building machines and analyzing data in pursuit of truths that might not have practical applications for generations, if ever. And it's about humility, acknowledging that the universe is vast and strange, that our understanding is incomplete, and that every answer raises new questions. We build machines like CERN because we want to know. We point telescopes at the sky because we want to see. We train AI systems because we want to process the flood of information and find the patterns hidden within. None of this is driven by fear. It's driven by wonder. And maybe that's the most important thing to remember. When people worry about CERN destroying the Earth or opening portals to hell, they're projecting fear onto something they don't understand. The reality is far more inspiring. We're a species that looks at the universe and asks why. We're not content with ignorance. We push boundaries, take risks, make mistakes, and learn. That's what makes us human. And it's why, despite all the dangers real and imagined, we'll keep exploring. Because the alternative, staying ignorant, staying safe, never asking, is worse than any risk. The universe is out there, full of mysteries. And we're going to keep unraveling them, one experiment, one observation, one discovery at a time. That's not something to fear. That's something to celebrate.